So thank you everybody for coming today. We're shifting gears a little bit and talking about space. So I'm part of a large group here at the museum. So Dr. Kim Tate is our curator, and then myself and Catherine Donnell are the technicians in the Earth and Space Department. Catherine looks after a lot of the databasing, and her passion is gemology, and my passion is analytics and answering questions with equipment to try and classify and describe everything that we have in the collections. And then we also have Dr. Phil McCausland, who is helping with our meteorite classification project. And throughout all of our work, we're really lucky to have the ability to work with so many great students. So Kim is a prof at, I think, U of T, Western, Queen's, and York. So that gives us great access to fantastic students in the GTA and Southern Ontario. And so that's how Josie came to be part of our lab group. This is her first year with the ROM, and we hope that she sticks around for a lot longer. But so Josie, Megan, Bennett, and Beth are all students that we currently have working with us in the lab. So first, to start off with, what are meteorites? So when these objects are floating around in space, they can be dust-sized to small asteroid size, but they're floating around in space. We refer to them as meteoroids. Whenever these objects then intersect with our atmosphere, start to pass through, undergo a lot of friction and heating, sometimes seen as shooting stars, we call these meteors. And it's only about 5% of the material that passes through our atmosphere that actually survives to land on Earth. If that happens, we call it a meteorite. So this is when this extraterrestrial rock actually lands on Earth. And where do these objects come from? So at the beginning of the solar system, when they first formed, they're widely strewn across the solar system. Big accumulations of them have clustered together in the asteroid belt, as well as just scattered about the solar system. And Jupiter kind of acts as a barrier between stuff from the outer solar system entering our region of space. But most of the fragments that we find landing on Earth come from this asteroid belt area. It's kind of leftover space debris all clustered together. And there's also, very rarely, but not unheard of, we do get material from Mars or the Moon. We don't think that we get much material from Venus because we think that the atmosphere is too much of a struggle to overcome. And there are some rumors that we get some things from Mercury, but it hasn't really been officially proven yet. So most of the time when we're talking about rocks from space, we're looking at things from the asteroid belt, and if we're lucky, Mars or the Moon. So on average, meteorites are far older and they're relatively unchanged over long periods of time long periods of time that Earth has had processes like plate tectonics undergoing. So plate tectonics is like the recycling of rocks on the surface of the Earth. Plates are subducting, rocks are remelting, there are different concentration processes happening, and our Earth is constantly changing. Whereas many of these objects in the solar system, once they first formed, after they initially cooled down, there wasn't a lot happening to them. So they're relatively unchanged examples of the first few 100 million years of our solar system. And we just don't have access to studying these processes that would have happened on Earth. The only way that we can learn more about our planet is by studying what is kind of trapped, almost as like a time capsule, from these other planetary objects. So very important for us to understand how our planet came to be. If, as a society, eventually we probably will spread out to other planets one day, we need to have an understanding of what's special about our planet, where do we find other similar planets, and these objects record solar system history that go back over 4.56 billion years. The oldest rocks that we've ever found on Earth are about, depending on who you talk to, it's rather controversial, about 3.8 billion years old. So this meteorites do hold a lot of information we normally don't get access to on Earth. And it also gives us understanding about the inner workings of our planet. So we, as humans, are probably never going to be able to drill down to the core of our planet to understand what the interior of our planet looks like, but by studying some of these objects that arrive that are examples of obliterated pieces of other planets, we can learn more about these inner processes. And then one of the most interesting aspects is that it's a tool in the toolkit for trying to identify where life originated in the solar system. So where do meteorites fall? They fall evenly all over the planet. So this is a map of bolide events from 1994 to 2013. They're pretty much evenly distributed all over the planet. But because Earth is 70% covered in water, we estimate that about 70% of all meteorites land in water. If you guys have heard the news article that was from about November or December of last year, November, so there was a meteorite suspected to have fallen in the Grimsby, Niagara region. You have a microphone, Josie.
Niagara.
The Niagara region. So there was a suspected meteorite that we saw come in through satellites. We know roughly where it would have fallen, but a large area of this is right over Lake Ontario. So we aren't too sure if we're ever going to recover material from that event, but we're very, very hopeful. But yeah, so 70% of the Earth is covered in water. That's where many of the meteorites fall. We do get hit by about 44 tons of material a day, but only 95% of that mass. So 95% of that mass incinerates. Only 5% of it actually lands. And most of the pieces that fall are about fist-sized or less. So it's very, very rare that we come up with big pieces of material. But even though they're falling evenly all over the Earth, we're not likely to find them in every situation. So we're more likely to recover meteorites from areas that are full of tundra or desert. So meteorites have to be found by people in order for us to recognize them and to be able to study them. If they fall somewhere that there are already lots of rocks or trees, we're far less likely to find them. So an example of this is even though Canada is the second largest landmass on Earth, there are only 101 meteorites that have ever been identified coming from Canada. Whereas if we look at an area like Northwest Africa or the Saharan Desert, there's more than 15,000 meteorites that have been found in that region of the world. So in our collections in museums, we often have a very big overrepresentation of areas that are quite desert or tundra rich. And this is just simply a collecting bias. We're more likely to find things in this area. It is really, that's why it's so important whenever we hear these news headlines of a meteorite falling in Canada and everyone rushes out to go find it, it's because they're pretty rare for us to actually collect. And at this point, once people find an object that they suspect is a meteorite, it makes its way to markets and to collectors, but it still hasn't been proven to be a meteorite. This is sort of the first step, is someone comes up with a suspected object and it now has to undergo testing. So there's a group of international volunteers who are meteoriticists, and meteoriticists is a bit of a mouthful word, but I think it's because the weather people took over the word meteorologist, so they got there first. International group of meteoriticists oversee all of the submitted meteorites. We have to actually prove to a group of scientists that we have a meteorite on our hands before we're allowed to call it that. We have to submit a whole bunch of data. They give it a stamp of approval, and only after that are researchers allowed to study it as a meteorite. Are we allowed to display it as a meteorite or loan it out and start to finally do some fun things with it? So we submit all of this data, and if it's approved, it gets granted a name, and we always name meteorites after the place where they've been found. And the ROM is really lucky because we're one of only 3 lab groups in the country that are capable of doing this process. So we get a lot of applications from people who have suspected meteorites to try and describe them. And this is how we actively build our collections, is to describe these meteorites so that they can then be researched and held in museums. So the ROM has one of the largest meteorite collections in the world. It's the largest museum collection in Canada, and we have over 14,000 registered specimens. We're very thankful to a very good donor to us who fell in love with the museum as a child, and he then became an avid collector of meteorites and has continued to donate a large number of meteorites to us every year, and his family is continuing to contribute as well. But our collection began in the early 1900s, so it's very representative of the history of our knowledge of these space objects. And just some highlights of our collection. There's about 100 or so known Martian meteorites that have ever been found on Earth's history. And the ROM is really lucky in that we have about a third of these objects in our collection. When we are trying to study whether or not life has existed on other planets, as Josie's going to talk about, we're one of the go-to places in the world where people can come and access this material, which is really important for future scientists. And some other highlights of our collection, this is Tagish Lake meteorite. It's one of the most sought-after meteorites in the world. It fell in winter of 2000 onto a frozen lake in British Columbia, and because it fell during the winter, it was collected and remained frozen the entire time. It's now in ultra-deep temperature freezers, and it has never been thawed or defrosted, and we believe that any carbonaceous material that would have been the early building blocks of life, like amino acids, have been totally preserved in these meteorites. So it's one of the most desirable things to study to try and figure out the origin of life on our planet. So you think you have a meteorite, but what do you do next? The very first steps is we take a look at it under an optical microscope. So we're looking for some distinguishing features. And if it passes the early test, it doesn't look like it's man-made in any way. It's probably a rock, we hope. Could be anything in the beginning. Then we carry on with handheld XRF. And so we get help from people like Laura in the museum, who I'm so glad was also presenting today, because now you guys also know Laura in the middle there. So she helps us out with a handheld XRF. So this is looking at the elemental composition of the rock. And we're looking for whether or not it has materials in it that would have formed in space. So if it has iron and nickel are the main things we look for, and then silicon and aluminum and calcium. But anything beyond kind of that initial range in the beginning is suggestive that it probably came from Earth. So copper is not a major component in space, lead, metals like that, zinc. So those would be some warning flags in the beginning that it's not a meteorite. And then if we want to proceed, we start to slice it open. So we have diamond wire saws in the museum that we use to cut faces into these objects. Whenever we finally approve a meteorite, we have to actually keep 20% of a meteorite as a type specimen in our collections for the rest of history. And we cut them with these special saws that we have in-house. And the things that we're looking for, some major features is that we want it to have no visible bubbles or flow marks, usually. So these are the examples that this would have been an object that cooled very quickly. Objects in space would have cooled very slowly over long periods of time. So if they have these examples, it's more likely that it formed on Earth. And another major feature we look for is a fusion crust. So as these rocks enter our atmosphere, they start to melt from all the friction, and that melting on the outside creates almost like a ceramic glaze. And that is a major distinguishing feature. We don't get that in terrestrial rocks at all, so we're trying to find this fusion crust. And once it passes this sort of initial sniff test, we're going to look for other types of features, trying to peg out what type of meteorite it might be. So if it's a very unchanged rock since the beginning of solar system's history, it might be a chondrite. So this is a rock that has very early pieces, very early spheres of glass and minerals that would have formed at the very beginning of the solar system and would have been quite unchanged. There would have been no thermal processes or heating that would have recrystallized the minerals that were present. And other objects that might have had some heating or change happen to them would come from differentiated objects. So if they were over about 100 kilometers in diameter, we would probably not expect to see any of these early spheres of glass. That's because melting would cause things like a core to form or the outer rocky layers to form. And so if we see things like this, the possibilities are it came from Earth, which is not so great, or that it came from places like Mars. So it's still pretty big possibilities. So we still have many things that we need to rule out. And the major types of meteorites that we can break things down to is if they're stony meteorites, so they're entirely rocky. If they're iron meteorites, they're entirely metal. And there are also meteorites that kind of fall in between in this region that are stony irons, and they're mixtures of metal and silicate material. But it gets really complicated if we keep going further, and if we want to prove that we have a meteorite, we have to narrow it down to exactly what type of meteorite it is. And so we have a whole bunch of chemical tests that we have to do to try and figure out where exactly in the solar system this rock would have formed. And it's quite amazing that some cases we only have maybe 5 grams of material, and with current levels of science, we're able to pinpoint exactly in the solar system where this object would have come from. And we use different types of microscopy techniques in the building to be able to do this. So I'm going to pass this on to Josie now, who is going to talk about how holding on to these objects has a big impact on her career here in the museum.
Hello, my name is Josie, and as was mentioned before, I am a master's student at the University of Toronto. As well, I'm working with the samples that they have here at the ROM. And working within the realm of planetary geology has always been my dream, and so I'm very happy and fortunate to be able to look at such amazing samples that they have here at the ROM. And it's been very important work as well. And I completed my my undergraduate degree in geological sciences at Queen's University, and working in research on an honors thesis is kind of what led me to where I am today. And with the ROM containing over 50% achondrites and rare planetary material type meteorites, it makes the collection one of the most important for planetary scientists around the world. And these samples that are the least understood and least studied today are the key to revealing the processes behind planetary formation and the potential signs for life on other planets. And so the type of meteorite that I'm studying is a Martian meteorite, which I think are the coolest kind. And these types of meteorites are brought to Earth by impacts that happen on Mars that send a piece of the surface projecting into space and into the direction of Earth, and they end up landing on our surface. And so this is the only way currently that we are able to study the geology of Mars, potentially, and as is being planned in the future with the Perseverance rover and the drill course that they're taking over there. By 2033, we might have some actual surface samples that hadn't been altered by flying through space and coming into our atmosphere, which will be very interesting work for the future. And so the aim of my work is to work on this Martian meteorite and better understand the processes of rock formation on Mars, the process of impact alteration on these samples, because when they come into our atmosphere, the heat and pressure, as well as landing, can alter the minerals, which I'll get into a little bit further, and as well as using the geochemical data that I collect from the sample to point towards potential biomarkers for signs of life on another planet. So the sample that I get to work on is NWA 6342, and as was mentioned, they're named based on where they were found. So NWA is Northwest Africa, and it was found in Algeria in 2010, and it was acquired by the ROM. And this specific type of Martian meteorite is called a shergotite, which can basically translate over to, on Earth, a basalt or a lava type rock. So this would have come from the Martian volcanic activity. It's about 175 million years old, and it had undergone about 60 to 75 gigapascals of pressure in its formation. And as you can see, there's 2 textural domains in this sample, poikilotic and non-poikilotic, very fun word, but these are just referencing 2 different mineralogical textures that are present that can form when this rock is formed. And what I'm studying specifically are the sulfides, as well as the shock in this meteorite. And as well, I'm going to be comparing this sample to other meteorite and terrestrial samples that are comparable in composition, all of which are provided by the ROM's collection, and most of which is in storage for preservation and research purposes, as opposed to the small selection of samples, relatively, that they have on display upstairs. And this work, along with much of the work done on these samples of the ROM, it's very important projects, including the characterization of sulfide and shock in the Martian meteorites. It's largely untouched topics in the scientific community, and specific to Martian meteorites. And being able to add new information to the limited collection that we have of knowledge of Martian geology is very impactful and is amplified through the acquisition of new samples as well at the ROM. And I used words like sulfide and shock, which might be new terms to some of you in the audience. And so basically shock or shock alteration is the changes that happen in the mineral chemistry of the rock and the minerals on microscopic and macroscopic scales when it's burning up in the atmosphere and when it lands on the Earth with a lot of heat and pressure, as well as sulfides are just minerals containing sulfur and at least one other metal. And that is the specific mineral that I'm looking at in this sample. And in order to study these things, I use a variety of imaging techniques, which you can see up there on the kind of confusing graph. And so I'll tell you a little bit about that more in detail. So this is where I work in the lab with this called scanning electron microscope, or SEM. And this is one of the various techniques I use to produce images like these. So on the bottom there, the colorful image is an element map where I kind of had overlain different elements by color. So there's iron, sulfur, and oxygen. And so that helped me, based on the colors kind of overlaying on top of each other, makes little yellow dots that are the sulfides. And so I use that as a target map when I look under the microscope. And this is from a thin section of the meteorite, so a really, really thin piece that was cut off. And so I get to look at these sulfides, and then you can get elemental weight compositions from specific targeted areas, and getting all of this geochemical data back can lead to petrogenetic conclusions about what this rock had undergone, what conditions it had formed under, and things like that, as well as potential conditions that relate to life being able to survive on Mars. And on top of this, I use a lot of other pretty fancy technology to get a lot more geochemical data. Some are just for more specific reasons or different elements or chemicals that you're looking into, as well as atom probe tomography, which is the one that is most different than these other ones. And that one looks specifically into sulfur isotopes, which is looking at the sulfur on an atomic scale in order to have interpretations specifically about the atmosphere that the rock had been formed under 175 million years ago. And atmospheric conditions are very significant when it comes to if life was able to survive or not on the Martian surface. And it doesn't have to be exactly like Earth atmospheric conditions, as life can survive under many different levels of extreme conditions. But getting that information is stepping stones towards potential life being able to exist on Mars. And so there's also other things that happen at the ROM that I am very happy to participate in, that happen around me while I'm doing my research. So having some of the most unique and diverse collections of meteorites and mineral specimens available to me at the ROM is a very great opportunity for me to access over 200 meteorite samples that are very rare, as I had mentioned, as well as study tons and tons of terrestrial samples that I can relate to my work. I also get to witness and participate in conference sample curations and other projects that the department's working on, as well as scientific outreach with my supervisor, Kim, Dr. Kim Tate there, who was being filmed for CBC, talking about the work that we do at the ROM as well. And not only is the quality of work that students are able to put out significant and unique to this institution based on the samples that we have, but also the caliber of students and researchers working at the ROM are drawn by the collection and seek to participate within this institution that's the best among the world. And so, as you can see, there's the drawer of all the Martian meteorites that I got to just look through, and it was very exciting to see all of these samples and see all the work that still can be done on them that hasn't been looked at. And lastly, I think my most exciting point is looking to the future and working at the ROM along with the amazing staff and my supervisor, as well as the people associated with the ROM and its collections have helped me to pursue my passion of understanding planetary geology. And I hope to take this unique set of knowledge and experiences based solely on the fact of the amazing collection that they have here, and work towards a career at a space agency or within the government or industry, and seeing the people that have come before me working on these samples gives me a lot of inspiration and hope for the research that will be happening in this country, and makes me proud to be a Canadian working on Martian meteorites. And so through my work at the ROM, I've been able to experience all this, so that has been amazing. And that's all. Thank you.